Okay, so this lesson will focus on the solubility aspect of equilibrium. So we're going to be talking about dissolving things in water and how equilibrium will apply to that situation. And we'll talk about the solubility product constant. It's a different type of equilibrium constant, but it's much the same thing. The trial ion product, and then finally we'll do some calculations involving the formation of precipitates. All right, so first off, I tell this story every time I teach solubility because I think this is a very good demonstration of what solubility is. So basically, when I was in university, on one of the nights, I had a really bad stomach ache. And the pain was so bad that I wasn't able to do anything else except roll in pain. And I knew that by going to the hospital, I wasn't going to get treatment anytime soon because it's just a stomach pain. You don't check into the emergency for something so mild. But because the pain was so hard to bear, I thought something was seriously wrong. So I did check into the emergency room, and I told the nurse at the kiosk I had a stomach ache. She looked at me and said, "Are you serious? Take a seat." I waited hours before the doctor could see me, understandably so, because it's a stomach ache. Eventually, I got in, and a nurse directed me to a room, and I got a hospital gown I was asked to put on. So later, a doctor came in, and she brought a beaker, like a straight up beaker, not a cup, like a 1 liter beaker of colorless solution, and asked me to drink it all. And I'm like, "Are you sure? Like all of it? Like, can't I just take a sip?" "No, you gotta like bottle up all of it. 1 liter of that." I was like, "What is it?" Because I wanted to ask. And the doctor was like, "Oh, I mean, it's a solution that will help us see your intestines for an X-ray. Because as you know, if you take an X-ray, you can reveal the bones, but the soft tissue will not appear on the X-ray very clearly. If you drink this, it will stain your intestines so that we can X-ray your intestines to see what's wrong." I was like, "Okay, cool." I drank the thing. I took a sip. It smelled, and it had this weird taste. It did not taste like water. It was disgusting. Oh, I couldn't even drink a liter of water in one go, but like I had to like take some time to drink that 1 liter beaker of nasty fluid. Now I know that I drank barium sulfate. Okay, but at the time I didn't know that. So I drank it. They took an X-ray, and they were like, "Okay, go home. No problem. It's a stomach virus. Goodbye." Well, I mean, can I have some medication? No, it's a virus. There's nothing we can do about viruses. Just go home. Your immune system will take care of it. I'm like, "Can you at least tell me what kind of virus it is?" Like, no, we're not going to bother running a test because that's not necessary. Just go home. I'm like, crap, I wasted my time. I drank that. So yeah, don't go to the hospital if you have a stomachache, folks. Anyway, when I got home, I realized that I drank barium sulfate. So I did some research, and I realized, hold up, the ions of barium sulfate are highly toxic. This is a routine thing for hospitals to give patients. Go ahead, drink this barium sulfate. The barium ions will stain your intestines so that it becomes opaque to X-rays. And I'm like, wait, this is not just a little bit toxic, highly toxic. And I didn't just drink a really dilute solution of barium sulfate. I drank a saturated solution. That means maximum ion concentration of barium sulfate. Now, why would the doctor recommend patients to drink deadly poisons? Well, the answer to that question has to do with this lesson. And hopefully, at the end, you will have a better idea of why exactly that is. How come I drank toxic ions and did not just die on the spot? It all has to do with solubility. Okay? So, solubility is actually an equilibrium. We learned solubility in grade 11, and we never talked about equilibrium, but it is an equilibrium. If you have a solid, you drop this in water and it dissolves, And if you happen to saturate the solution, that means not everything will dissolve. You will reach the maximum ion concentration, and a solid residue called the precipitate will be left behind. And this is the equilibrium. The solid is not just sitting there. It is constantly being dissolved by the water into ions. But at the same time, the ions will constantly come back and form the crystal again in an equilibrium reaction. So when you reach maximum ion concentration, that is saturation, really what happened was the rate of the forward reaction is equal to the rate of reverse reaction. Okay, the barium sulfate dissolved in water at saturation, you have a double arrow. The forward reaction we call the dissociation reaction because the solid breaks apart, dissociates into ions. And the reverse reaction is called the recrystallization reaction. Ions will come back and remake the solid crystal. Okay, so when they're equal, you have a saturated solution. All right. Now, the solid is said to be in equilibrium with the ions only if it's saturated. If you're not saturated, that means you can still dissolve more. Okay, if you drop salt in water, just drop a little bit of salt, you swirl it around, you're not going to see anything because all the salt will dissolve. That is not equilibrium. That is just straight up dissolved. But if you add so much salt where solid start to form because it won't dissolve anymore, that is equilibrium. So a saturated solution is something that can't dissolve any more ions. It has reached the maximum concentration available under those conditions. We learned Le Chatelier's principle. If you change the conditions, you will dissolve more, but if you keep them the same, it is saturated. Molar solubility, I'm just defining this term so that I could use it later on. Molar solubility is the ability to dissolve a solute. How much can you dissolve in moles per liter? So it is a concentration in moles per liter. It tells you what is the concentration of the ion in the saturated solution. That is your molar solubility. The higher the molar solubility, the more soluble you are, obviously. The more ions will be present at equilibrium. And also, this, like all other equilibria, it is affected by temperature due to Le Chatelier's principle. Okay, so changing the temperature will change solubility. It could either increase the solubility or decrease the solubility. It depends on whether the dissociation reaction is endothermic or exothermic. All right, because we're still studying equilibrium, there's going to be KEQ. Right, you can write the KEQ for this reaction here, the solution of barium sulfate. The KEQ, as you recall, is all the products divided by all the reactants. And there you have it. The product, barium ion times sulfate ion, divided by reactant. But wait, the reactant is a solid. Okay, we do not include solids and liquids in our KEQ expression, so that's gone. And notice I didn't write KEQ, it's KSP. KSP is exactly the same as KEQ. In fact, it is KEQ for solubility reactions. We just decided to call it a different name. This only applies to solubility. So it's called the solubility product constant. Exact same meaning, only applies to solubility. So there's literally no difference. What does that really represent, though? It represents the concentration of the ions at saturation. If you just look at the mathematical equation for this, it is equal to the products of the ions that are present. You multiply all the ions together, there you have it, that's the KSP. Meaning that if you have a lot of ions at saturation, you have a high KSP. If you have very few ions at saturation, you have a low KSP. That means high KSP equals high solubility. You can predict how soluble something is. If you just look up its KSP, if you see a big number, oh, this is very soluble. Low number, you're not soluble. Okay, so far, any questions? Alrighty. So to write the KSP expression, it's the same thing as KEQ. Iron 3 hydroxide dissolves into iron 3 plus, and 3 hydroxide. So the KSP will literally be iron times hydroxide cubed. The cubed because there's a 3. And silver sulfide, equilibrium, silver and sulfide ions. Because you have 2 silvers, you have 2 silver ions. The KSP, you square the silver. The sulfide remains the same. And lastly, you have calcium phosphate. If you balance the equation, you have 3 calcium ions and 2 phosphate ions, and the KSP will be exactly as you expect. Calcium cubed, phosphate squared. The solid is never present. The convention is the solid is on the left side of the equilibrium arrow, and the ions are on the right side. So the forward reaction is always the dissociation reaction. The reverse reaction is the recrystallization reaction. That's just the convention. All right. KSP will therefore be just the ion concentrations multiplied together. If you flip the equation, technically it's still right. It's just that the KSP wouldn't match. You have to put the KSP under a fraction. You flip it to the power of -1. Okay, so we don't do that. So make sure that in your calculations and when you write these equations, the ion concentrations are on the right, the solids are on the left. So let's look at some examples with solubility. So example 1 asks, calculate the molar solubility of silver sulfide in moles per liter at 25 degrees. The KSP of silver sulfide is 6.31 times 10 to the negative 50 at 25 degrees Celsius. First of all, just look at the KSP. Look at how tiny that thing is. 10 to the negative 50 is unimaginably small. Right? That is a lot smaller than Planck's number, which is 10 to the negative 34. Okay, this is beyond the scope of our imagination on how small this is. So this tells you that silver sulfide, for all intents and purposes, does not dissolve. But we never say that. You can't say that it doesn't dissolve because on the molecular level, some of it dissolves. It's so tiny that we just say, oh man, I don't see it. Okay, everything dissolves. Even sand dissolves. It's just that it dissolves very little. It makes no significant difference. We just say, okay, you might as well have not dissolved. So silver sulfide is very insoluble, but you can still have a calculation with saturation. It's just that the ions of silver sulfide at saturation is so low that it might as well not be there. So let's do this question. Write the dissociation equilibriums. Okay, silver sulfide breaks into silver ions and sulfide ions. We did that on the previous page. All right, so there is still an equilibrium present. It's just that the ion concentrations are pathetically low. Write the KSP expression, well, silver squared times sulfide. Okay, so far makes sense? Now, you can draw an ice table to help you find the answer. You want to calculate the solubility in moles per liter, right? Initial concentration of the ions before you dissolve this. If you didn't put it in water, what is the concentration of silver and sulfide? Can somebody tell me?
Zero?
Yeah, 0. You didn't put it in, so of course you don't have any. Initial concentration will be 0 because you didn't dissolve. Make sense? All right, what about the change? Well, we don't know. So X. So 2X for the silver, 1X for the sulfide. It must go up. You can't go lower than 0. Final equilibrium, well, that's just 2X and X. You can see that the ice table is kind of moot here. It's useless. As long as you know that it's 2X and X, you don't really need to draw an ice table. I drew it for good practice. And I crossed out the column with the solid because the concentration of a solid is not subject to change. So we just ignore that altogether. So really, just know that the equilibrium concentration is 2X and X. It's time to solve for X. Okay, you could use the KSP formula to solve for X. KSP is 2x squared times x. The concentration of silver is 2x. So if you want to square that, you got to square the whole thing, not just the x. You got to square the 2, which is why you have the brackets. KSP is this small number. 10 to the negative 50 equals to 4x cubed. A very simple calculation. You just take the cube root of that number, move the 4 over, take the cube root. You would have 2.51 times 10 to the negative 17 moles per liter. This is so tiny. Okay, to put it in perspective, a really strong acid, a really concentrated strong acid like sulfuric acid, let's say, the acid found in car batteries has a pH of 0. You put your hand in it, you can say goodbye to your hands. That has a concentration of hydroxide, the base, of 10 to the negative 14. All right, it's that low. It is near 0. We just say it's 0. If that's 0, then this is 0. Might as well not exist, but still something. So that's x. What is x? X is the change. You can use x to solve for molar solubility. Here's your balanced equation, right? X is the change, but that is also the sulfide ion, because that's literally x. But since sulfide and silver sulfide is a 1-to-1 ratio, they should have the same x. I'm talking of the aqueous silver sulfide, not the solid. This is asking for the solubility of aqueous silver sulfide. How soluble are you? Well, here's your number. Same number, 2.51 times 10 to the negative 17 moles per liter. At saturation, that is your concentration, which is pretty much 0. Okay, does that make sense, everyone? You can see that this is the same calculation we did in the last class. It's just that it has a solubility flavor to it. Okay, that's pretty much it. Same math, same steps. Here's example 2. Work on example 2 on your own, and then I'll take this up. Calculate lead 2 plus and iodate 2 plus ions. Sorry, iodate 1 minus. In saturated solution of lead 2 iodate at 25 degrees Celsius. Okay. There's the KS. All right, so here's example 2. You need to calculate the concentration of both ions. So you're given the KSP, so you can use the KSP formula to solve this. So first you need the balanced equation. The solid always goes on the left, so lead 2 iodate, so PbIO3 bracket 2. It becomes lead 2 plus and 2 molecules of IO3 minus. So the KSP will be lead times IO3 squared. You have initial concentration of 0 because you didn't dissolve yet. X for the change, so X and 2X. And then your equilibrium is just X and 2X, okay? So here is the KSP. You substitute X and 2X. So that means you plug in the KSP, 3.7 times 10 to the negative 13 equals to 4x cubed. You can solve for x using algebra. Just move everybody over, take the cube root, calculate that, and you get 4.5 times 10 to the negative 5 moles per liter. That's what x is. X is the change in concentration, but also x is the concentration of lead because it only has one x. So that is literally the same thing. For the iodate, you just need to double that. And so that becomes 9.0 times 10 to the negative 5. If you get these two, you're done. That's all the question wants, the concentration at saturation of those two ions. All right, is that clear, everyone? Okay. Example 3 is a little different. Example 3 says magnesium fluoride is a hard, slightly soluble salt that is used to make spectral lenses for technological or technical instruments. Totally useless sentence. Calculate KSP for magnesium fluoride at 25 degrees Celsius given a solubility of that number, grams per 100 milliliters. So this question is different. It asks for you to solve the KSP. You are given the concentration, but the concentration for the solubility is given to you in grams per milliliter. You can't have that. You have to have moles per liter. So here is where your grade 11 chemistry skills come in. I'll give you around 5 minutes again. Try to solve this. You have to convert the grams per mils into moles per liter in order to do this question. And then you set up the ice table, the KSP expression. You should get the KSP. All right, so I'll give 5 minutes. All right, so for example 3, same thing. You have to eventually get to the KSP expression, meaning that you have to find the balanced equation. So magnesium fluoride, MgF2, you have to know that magnesium fluoride is MgF2. I won't give you that information because it's too simple, grade 10 naming. And then that will dissociate into magnesium 2 plus and F2 minus. So KSP will be magnesium times fluoride squared. Problem, I need concentrations of these two ions in moles per liter. I'm given the concentration in grams per milliliter. So first, you have to convert. You start with grams per milliliter. You stack them together on a fraction. Very nice and cozy. And you convert the grams to moles, and then you convert the milliliters to liters. So this is really just a conversion problem. If you divide by the molar mass, the grams should cancel with the grams. Okay, and then you would have moles. But right now you still have milliliters, so you multiply by 1,000 milliliters over liter, so the milliliters cancel. So the units left will be moles per liter. And you put that in, and there you have it. That is the concentration of magnesium fluoride aqueous in moles per liter. So you start to fill out your table. 0, 0, because in the beginning, nothing dissolves. You have x and 2x, and then finally, same thing, x and 2x. That's your ice table, which is kind of unnecessary. All you need to know is x and 2x. You multiply them together, and you have to square the 2x. Because MgF2 has the same mole ratio of 1:1 with Mg, that is also equal to x. Okay, you see the logic here? We solve for the concentration of MgF2, and that is equal to the concentration of magnesium 2 plus because it's a 1:1 ratio. So that means that must be x. So x is equal to 2.76 times 10 to the negative 4 moles per liter. It is time to substitute into the KSP equation. So there's the KSP equation. You can sub in x, so x times 2x bracket square. So KSP is 4x cubed. What is x? You substitute the value of x. You put this in your calculator. You should find the KSP, which is 8.41 times 10 to the negative 11. And that should be the final answer for this question. Okay, any questions before we move on to the next part of the lesson? All right, so the next part of the lesson will get more complicated because you're involving a mixture of two different solutions now. If you mix two solutions together, you may or may not form a precipitate. It depends on the KSP of the ion combinations. If one of them has really low KSP, then that one is likely to be your precipitate. Okay? So this is a really pretty but expensive reaction. Silver nitrate is highly soluble, AgNO3. Okay, it's a colorless soluble solution. You mix that with also a soluble solution of potassium chromate, which is a yellow solution. When you dip them together, they will quickly form a crimson red precipitate. right, as demonstrated by the image on the right side. So that's why I say this is a very beautiful reaction. You make this beautiful red color, which did not exist in either of those reactants. And there's a precipitate too. So that means some combinations of ions made a precipitate. So let's investigate. So there are 4 different ions in here. You have silver ions and nitrate ions from the AgNO3. And then you have the potassium ion and the chromate ion with the K2 CrO4. So which combination gave the precipitate? Which combination of ion will give you something with a low solubility? You can do that by referring to a solubility table. Okay, in grade 11, we learned how to identify whether something is soluble or not using a solubility table. In grade 12, we do much the same. You have a solubility table in your data booklet. So all you have to do is refer to that table and see which combination of ions would give you a soluble solution, and which ones will give you insoluble precipitate. Okay, I realize now there's a small problem because look here. Here's your solubility table of the one from, I believe, your booklet, the data booklet. Very funny. I didn't notice when I did this. The chromate ion is actually not found on this table. But let's just try to use the table anyway and see what happens. How would you use this table? Well, you identify your ions. There was a nitrate ion, silver nitrate. Here is the nitrate ion, right? Okay, cool. Nitrate is soluble with most according to this table, okay? In the second row, it would say what that ion is soluble with. And in the third bottom row, it will tell you what are the exceptions to this. So nitrate is soluble with, in fact, everybody. Because no exceptions include a nitrate. So nitrate is always soluble. Make sense? That's why silver nitrate is soluble. All right, let's look at potassium. Potassium, K, is a group 1 ion. And guess what? Group 1 ions are all soluble, it says most. And the only exceptions are rubidium with perchlorate, cesium with perchlorate. Everybody else will be soluble. Okay? So that means potassium is soluble with chromate, because chromate is not listed there as an exception. So you know that potassium nitrate has to be soluble. What about silver and chromate? Usually this one lists the negative ions on the top. And if you scan across the top, oh wait, I don't see a chromate, CrO4, that's not there. So this table actually doesn't have chromate. It doesn't have all the negative ions. It's a sample of the most common ones. Yeah, I happened to choose chromate because I thought the color was beautiful and I didn't realize it wasn't on this table. So, well, if it's not on this table, you're not sure. So, which is why I'll tell you 2 rules. If you remember these 2 rules, for 90% of the questions, you won't need a table in the first place. Rule number 1, nitrate and alkali metals are always soluble. The same with NH4. Group 1, the alkali, NH4, ammonium, and nitrate. They are always 100% soluble with everybody. Okay, does that make sense? If you see a nitrate with anything, say no more, it's soluble. Second, silver is never soluble except with nitrate, because nitrate is soluble with everybody. So silver is only soluble with nitrate, and it won't be soluble with anything else. Those are the 2 rules that I happen to remember. So for 90% of the solubility question, I don't have to look on the table because just refer to the rules. So in this case, silver will not be soluble with chromate because chromate is not nitrate. So by the process of elimination, we conclude that it must be the silver chromate. That combination is insoluble. So here's the balanced chemical equation. This is a double displacement reaction. Silver nitrate plus potassium chromate. You react. We now use equilibrium signs, not arrows anymore. So that is silver chromate solid. Okay, that is the precipitate. And potassium nitrate aqueous. You balance the equation. You put a 2 on the silver, a 2 on the potassium nitrate to balance everything. So now let's look at the complete ionic equation. Well, here it is. All you have to do is break the aqueous into individual ions. This is also a review of grade 11. You have 2 molecules of silver nitrate, so that will split into 2 silvers and 2 nitrates. Okay, the potassium chromate, it will split into 2 potassiums and 1 chromate because it's aqueous, it will break apart in water. You do the same thing for the products. The potassium nitrate, there's 2 of them, so you split into 2 potassiums and 2 nitrates, but the silver is a solid. If you are solid, you're trapped in a crystal, you don't dissociate. That's why you are solid. So you keep it as it is. You don't split that up. And we learned in Hess's law, you can cancel stuff. If you find the same ions on the left and the right side of the equation, you can just cross them out. So what do we have left? You have the silver, the chromate, and the silver chromate. The silver chromate being a solid, it is the only solid present in this entire equation. That is the precipitate, okay, the solid. And the things we crossed out, we call them spectators. These guys, they showed up, they did nothing, and that was the end of it. They did not contribute to anything in the reaction. They basically appeared. Hence, spectators. Before the reaction, you're there. After the reaction, you're there. Thank you for coming out. Okay. The rest of the reaction did occur. So the net equation, if you just cross out all the spectators, you have 2 silvers plus chromate ion, you get silver chromate solid. That is the ionic equation. But look, the solid is on the right side. The ions are on the left side. That's a big no-no, so switch them. You now have silver, chromate, the solid, on the left side. That's the convention. The dissolved ions on the right side, so that the forward reaction is dissociation. You have to write the equilibrium dissociation equation. You have to do this step. If you don't, you're going to screw up because the KSP will always be referring to this, the products, as ions, not the reactants. Right, so that's how you would determine whether a precipitate exists and how you will write the dissociation equation. Any questions, guys? Okay. KSP is therefore silver squared times chromate. Okay, so you need this skill in order to proceed with the more complicated examples. All right, so the trial ion product is represented by Q. This is the same Q that we learned in the previous class. Okay, it is just the same as the K, except you don't have to be at equilibrium. So you can have the trial ion product calculated from the initial concentrations without them being in equilibrium, and then you can compare this Q to the K value of the KSP, and then you can then figure out, will this form a precipitate? How would that work? If you multiply all of your ions together, like you would for the KSP, but except it's not in equilibrium, so Q, and if you get a huge number, this is bigger than the KSP. This means that you have way too much ions. Okay? You have excess ions. The concentration is too high, so therefore equilibrium will shift to the left to make more solid. They will form a precipitate. If Q is greater than K, precipitate forms. If Q is equal to K, then you have this magic moment where you just reached the equilibrium, but you didn't form the precipitate yet. You're just beginning so no precipitate. All right, so the sign of Q when compared to the K will tell you whether a precipitate forms. Let's look at example 4 then. How to determine whether a precipitate forms. So you mix two things together. 25 milliliters of 0.05 moles per liter of sodium carbonate and 25 milliliters of 0.002 moles per liter of calcium nitrate. You mix them together at SATP. Now, it's important that I mentioned SATP because you have to specify the conditions. Otherwise, you can't do this. So will a precipitate form? Yes or no. It's a yes or no question. You have to prove this mathematically. All right, so to do this, step 1, identify the possible precipitate. Which combination of ions will give you a precipitate? You have 4 possibilities, right? Sodium carbonate, calcium nitrate, calcium carbonate. You can quickly realize that it's calcium carbonate. Why? Just use elimination. Sodium carbonate is given to you as the reactant. I straight up told you the volume and the concentration. So it's got to be soluble. That's not it. And by the way, sodium is soluble with everybody. So there you have it. Same thing for the calcium nitrate. I straight up told you that that's a reactant in solution. So of course it's soluble. You have the concentration and the volume. And of course, nitrate is soluble with everybody. So that's not it. If sodium is always soluble and nitrate is always soluble, sodium together with nitrate, that better be soluble. So no, that's not it. So that leaves calcium carbonate. In fact, that is chalk. That is what limestone is made of. So, okay, that is not soluble. So that is your precipitate. You see, I didn't use the table. I just used common sense because I memorized those 2 rules. All alkali metals are soluble. All nitrates are soluble. All silvers are not soluble except for nitrate. All right, so once you find your precipitate, you write the dissociation equation for that precipitate. So calcium carbonate will slightly dissolve to make calcium ions and carbonate ions. Again, remember, everything dissolves. Even sand can dissolve. It's just different things dissolve to different extents. Just like every bond is both ionic and covalent, it depends on the electronegativity difference. One is more ionic than the other. So same thing here, it's a spectrum. It's not black and white. So this will also dissolve to a small extent. That's the equilibrium. All right. How do we solve for whether there's a precipitate with that? You need the KSP. And you need to compare that to the Q. Right? How do you find the Q? Well, you need the KSP equation. But you need concentration in order to plug in the numbers. So what are the concentrations of calcium and carbonate? I'll tell you right now, it is not those numbers given to you in the question. Because think about it, guys. The question says you mix 2 solutions together. So the question gives you these separate concentrations and volumes before you mix them. But after you mix them, first of all, the volume would be the sum of both. The concentrations will be diluted. Because you added more volume, concentration goes down. So you need to calculate the new concentrations after you mix them together before it reaches equilibrium. So how would you do that? How do you calculate the diluted concentration after you mix them? Think back to grade 11 chemistry. Okay, you learned this in grade 11 chemistry. CV equals to CV. The concentration of the dilute multiplied by the volume of the dilute, so after you mix them together, it is equal to the concentration of the concentrated before you dilute it, multiplied by the volume of the concentrated before you dilute it. CV equals to CV. Okay, this is the formula we learned in grade 11. Please know this. If you don't remember, well, now you do. There's the formula. And because we want to calculate concentration after you mix them together, that would be C dilute. That's the one that we want. So you can isolate for that term. You move the V over to the other side. You apply this formula to calculate the concentration of the ions that we care about after you mix them together. Okay, do you guys follow? So who do we care about? The equilibrium ions, obviously. The one in the precipitate, calcium and carbonate, because those two will make the precipitate. So we need to know the concentration of calcium after you mix them up. You can do that by using this equation. Where do you get the calcium from? It comes from calcium nitrate. Okay? You can apply the formula to calcium nitrate to get the final diluted concentration. See, concentrated. The initial concentration of calcium is given to you 0.002 moles per liter. Well, actually, the question gives you the concentration of calcium nitrate, CaNO3. It doesn't give you the concentration of calcium. But you can, extrapolate. It's a 1-to-1 mole ratio. It's got to be the same. So it's still 0.02. The volume of that is 25. It says you mix two 25s together. So individually, you're 25. The total volume after the dilution is just the sum of the two, so 25 plus 25. You do the math, it is 1.0 times 10 to the negative 3 moles per liter. That is the dilute concentration after you mix the two things together. Okay, does that make sense? This didn't achieve equilibrium yet. You just mixed them together. You diluted them, no equilibrium yet. This is initial diluted concentration. You, of course, do the exact same thing for carbonate because you need to know both. Where do you get the carbonate from? From the sodium carbonate, of course. So you take the sodium carbonate equation. What is the concentration of sodium carbonate? 0.05 given to you by the question. By extension, carbonate, which is a 1-to-1 ratio with sodium carbonate, also is 0.05. The volume of that, 25, that's given, divided by total volume, which you mix them together to be 25 plus 25, and you have 2.5 times 10 to the negative 2 moles per liter of carbonate. After you mix the two together, it's now diluted to a smaller number. There are two sig figs, but I included a third figure to make that more precise. Okay, any questions about this part? All right. You have to realize that these two numbers that we just calculated are the diluted concentration after you mix the two things, but it didn't reach equilibrium yet. It takes time to reach equilibrium. When you just mix them, that is non-equilibrium. All right, so these are the initial conditions. So if you multiply them using the KSP formula, because they're not yet at equilibrium, you are not calculating the KSP. You are calculating Q, the trial ion product. So you put them together, boom, you have 2.5 times 10 to the negative 5. That is your Q. Finally, last step, you can compare Q to K. The question doesn't give you K because you're supposed to have a table. You can just look on the table for the KSP of a lot of stuff. So look on the table for the KSP. Well, actually, you don't have a table. I never gave you the table. The booklet I found online, it doesn't have a KSP table for some reason. So on the test, I'll just give you the KSP every time so you don't have to flip through and look. If you just look on the table, you will see that the KSP for this reaction of calcium carbonate is 5 times 10 to the negative 9 at SATP. So compare K to Q. Well, Q is 2.5 times 10 to the negative 5. 10 to the negative 5 is bigger than 10 to the negative 9. A lot bigger. So Q is bigger than K, therefore a precipitate will form because you have way too much ions. And that's it. So do we have any questions? That was a long calculation, okay? Many steps with many little things to take note of. Here is example 5. Please take some time and work on example 5. Exact same type of question. Will a precipitate form? So would a precipitate of lead 2 sulfate with that KSP given to you form if 255 milliliters of that concentration of lead nitrate is poured into 456 milliliters of that concentration of sodium sulfate? So yes or no, would there be a precipitate? And back it up mathematically. So 5 to 10 minutes, and then I'll take this up, and that should be a wrap. Okay, last example. Is there a precipitate? First of all, you have to identify the possible precipitate. Well, no, duh, the question literally tells you is lead 2 sulfate, so you can just skip that one. The dissociation equation, well, it's just lead sulfate breaking into ions. All right, so now calculate the diluted concentration of the lead 2 plus and the sulfate 2 minus using the dilution formula. So there you have it on this page. For the lead, the initial concentration of the lead nitrate is 0.00016. Initial volume is 255 divided by total volume, and boom, 5.7 times 10 to the negative 5. I kept 3 extra digits for accuracy. And then the sodium sulfate, you have the sulfate concentration ion to be initial concentration 0.0023 times a volume of 456 milliliters divided by total volume, and boom, 1.4 times 10 to the negative 4. You have these two numbers, which represent the initial concentrations before equilibrium. After you mix them together, before equilibrium. You can now use them to calculate Q. Okay, Q is just a product of these two. Boom, multiply them together, you have 8.5, now you can round to sig figs, times 10 to the negative 9. What is K? Well, K is 10 to the negative 8. So in this case, Q is actually smaller than K, because negative 9 is smaller than negative 8. So therefore, you don't have enough ions, and a precipitate will not form. So the answer is no. Okay, but on the test, you have to show me what Q is. You can't just say yes or no. It's not a 50-50 question. You have to prove it to me. Okay? And that's it. This is the class for solubility. We learned what solubility equilibrium is. We learned the KSP. We learned the trial ion product. We learned how to calculate whether a precipitate will form or not using Q and the KSP. And that concludes this part of the unit. This will be the last lesson before the test. Any questions? All right.